So we've been working with exponents. We know what they are, right? An exponent means to do what? Multiply over and over again, right? How many times? Well, whatever the exponent number is, that's how many times you multiply something by itself, right? And you've seen some of the problems here that certain things can grow, as we say, exponentially. How about the rumor problem in the homework? Would you say that that rumor grew exponentially? Yeah. Because every day it got multiplied, right? And the number of days the d was in the exponent, okay? So that grew exponentially. And things can also decay exponentially. In your science class, have you ever heard of exponential decay?
No.
Okay, some of you have, right? Radioactive half-life, maybe?
What is that?
You'll learn about it, don't worry. So, like, if something keeps going, what if some amount of stuff that you have gets cut in half every day? Would that be a decaying amount of it?
Yeah.
You start with a certain amount, each day it's half that, and then half of that is left, right?
Like
Right?
decomposition?
I don't know what that means, but. So, exponential growth and decay. That's what we're talking about here. So exponential growth and decay. It's going to look roughly like this. Y equals A times B to the X. Okay? And again, the variable is in the exponent. Okay? Maybe you gathered that this A would be the starting amount of something, right, that's either growing or decaying, right? Wasn't that the y-intercept we talked about in the homework? Yeah. Right? The first day of the rumor, 20 people knew, right? And then it may double every day or get cut in half every day or something like that, right? Okay. Let's look at an example, see if we can put one of these exponential growth models together. Well, that's another rumor. Okay, same thing. The thing with the rumor, right? So let's say Wheeler here knows a rumor, and then she tells two people, right? And then each of those two people tell two people each of their own, right? Right? Isn't that exponential growth? It just keeps branching out very quickly. Doesn't you start to grow and climb? Like the further you went along, the faster it would climb, wouldn't it? Because more and more people would know it.
Yeah.
The only thing it assumes, though, I will say this: can anybody think of why the model they're talking about here might not quite work out the way they think? Like maybe not completely double each day the number of people know.
Yeah, because not everybody is going to tell one other person, or some people might tell like 4 people, like 3, you know.
Right, or of the 2 people you tell, one of them may already know, right? There's overlap. So anyway, but they're assuming that it's just like new people each day. So a number of people have heard a rumor, it grows exponentially. It's in a rumor that starts with 3 people, right? Hey, wouldn't that be like the A in this thing here? Yeah. Like the 20 in the homework, right? Where the number of people have heard it doubles each day, so it gets multiplied by what? 2. And the next day, times 2 times 2. And the day after that, times 2 times 2 times 2. You see where an exponent will come in here? Okay. Huh?
We really could do so much better. But why? That's why the rumor is good? Yeah, because...
Sure, we should work on our rumor spreading.
Yeah.
All right, part A. Why does it make sense that the number of people who have heard the rumor would grow exponentially? We were just talking about it. Why would that make sense? What does each person who knows about the rumor do? Tell other people. And then what happens? All of those people tell more people, right? So how do we write that down? We might say each person who knows tells other people. Each person who knows tells other people, right? And they each tell other people, and they each tell other people, etc., right, and so on, okay? Just keeps ballooning. Let's take a look at part B. They want us to fill in a table here. So the number of people is going to be that capital N, yeah? And what does the D stand for? Yeah, there was really no way to know what D would stand for. What is there? Okay, you read, right? Okay, so on day 0, the day it started, right? How many does it start with? 3. And then on the next day, right, they're going to call it day 1. What happens to the number of people? Doubles, right? So this is times 2, isn't it? And then the next day, isn't it again times 2? So what do we have? And then times 2, 24. Next day, multiply that by 2 again. What do you got? 48. And then again times 2, you get what? 96 people, right? On the 5th day after it started. Okay. So that times 2 times 2 times 2 could kind of be handled with a what, maybe? An exponent, right? It's repeated multiplication, yeah? Okay. Exercise 2 is really continuing exercise 1. So we'd like to know the number of people who know the rumor in 20 days. I don't want to fill out a chart and go out 20 days or 100 days, do you?
Yeah.
Well, you know, just like when you have a number to add over and over again, you'd rather do what to that number? Multiply. If you have numbers to multiply over and over again, you'd rather use a what? An exponent, wouldn't you? Okay, so let's set something up here. So for the following number of days, fill in how you calculate your values. All right, well, we kind of got that. So when n equals 3, day 0, number of people who knew equal 3, right? Wasn't that going to be, what the heck, right there? Right there? Yeah. Right, so that equals 3 times 2 to the 0 power, isn't it?
Yeah.
What is 2 to the 0 power? Taken, we don't need to be on the calculator right now. Just set them aside. 2 to the 0 is 1. 3 times 1 is 3. Okay? And then on the next day, right, we've got 3 times 2 to the first power, which is what? 3 times 2 is 6, right? So think of it this way. This is 3 times 2 0 times, isn't it? And this is 3 times 2 once. And the next one will be 3 times 2. Yeah, right? So this would actually be 3 times 2 to the second, right? Which equals, what's 2 squared? 4. And 3 times 4 is 12, right? Follow me? What about down here? This would be 3 times 2 to the what? What's 2 to the third?
8.
3 times 8, which is, use your fingers.
Oh, yeah.
So 24 people, right? On the 4th day, it'd be 3 times 2, 4 times 2. That makes sense, right? What's 2 to the 4th? 16. And then, but the 3 times 16 is 48, right? And then on the 5th day after the rumor, 2 to the 5th. What's 2 to the 5th? Isn't it just going to be doubled 16? Which is 96. So it matches our table, right? So maybe we can put a formula together here, yeah? Okay. So over in part B, let's put a formula in here. So instead of y, we'll do our function notation. So it'll be the number of people who know as a function of what input? Days, right? So n, the number of people who know as a function of days will equal, well, what was the starting amount of people who knew the rumor? 3. And what happened to that number of people that knew? Got doubled how many times? Whatever the number of days is. 3 times 2 to the whatever the number of days is. Uh-huh.
The teeth power.
Sure, yeah. Steve Power. Okay? All right. So they want to know how many people would know on the 20. After 20 days. So we put in what?
20. 20.
So it would be n of 20 equals 3 times 2 to the 20th power. Now on your calculators, let me show you how you can do that, right? Actually, I want to give you a quick note here first. So let's go to the notes page for a moment. Make sure. So exponents on calculator.
Oh, windmill.
Hmm? I mentioned a caret key yesterday, right? Looks like this. It's basically an exponential key, right? So if I want to, I'll give you some examples of how to put stuff in the calculator. If I want to do 3 to the 4th power, right? Here's how I type that in. 3 caret 4, and then I hit enter. Right? So everybody try that. Just use Scratchpad, the first one where you calculate. So hit your little Scratchpad.
Hold on. Can you go back to the notes?
So push this little button right here once. And it should come up to the screen that looks like this. It says Scratchpad. Okay. So now type 3. And then you see the caret button here. And you want it to the 4th, right? And then hit enter.
81.
81. Okay? So 3 to the 4th, it equals 81. Let me show you how to enter some other things. Let's try 1/4 to the 3rd power. Now, listen, hey, everybody pay attention. This is how you're going to enter this, okay? You're not going to use whatever stupid fraction. No, you're not going to do it that way. You're going to put parentheses, 1 divided by 4, close your parentheses, right? Caret button, 3.
164.
So let's try that. So parentheses, 1 divided by 4. Now you got to move outside the parentheses here. Everybody see, look. Hit the right arrow button or the other right. Caret button. You got to get outside the, what do they say, the 4th? 3rd? Like that. 1/64. Okay? What if you wanted the decimal, by the way? So we could do, let me enter that again. Instead of hitting enter and getting the fraction, you could hit control enter. Try that. The regular enter button, if it can put it in a fraction, it will. But if you really don't want that, you can hit control enter.
0.01.
Yep. Okay, so that was 1/64. Okay. What about -5 to the 3rd power? What do you absolutely have to have in there?
Negative.
Yeah. But the parentheses, right? Because without the parentheses, the negative doesn't get applied to the exponent, right? So it'll be parentheses, -5, close parentheses, caret 3. Go ahead and do that. What do you got?
-125.
Wait, I thought we should get a positive.
Oh, it's an odd number on that.
Oh, it's an odd exponent, yeah. All right, so it'll be -125. All right, so you got a feel for how to do these on the calculator now?
Yes.
All right, let's go back then. Got this? Nice. Hold on the calculator for a second. Well, we'll use them here. Let's go back to this problem here. Now let's put this in our calculator. 3 times 2 to the 20th.
300, 100, oh, 300,000, 14. Wait, I don't even know how, that's a big number. 3,145,728.
3,145,000. Whoops. Got the one.
That's a lot of people. That's a big school.
728 people.
I wonder how many people are in the population of America.
Do you wonder
Like
that?
8 billion.
Yeah.
No, that's the whole-
That's population of the world.
No, I feel like
About 360 million, I think.
Yeah, so 6 times that. That is 6.
Well, that's-
Um,
Guys, that's less than 3 weeks.
that is
wait,
1/6 of
How
the
many people does the
population.
rumor start with? 3. And in less than 3 weeks, it's over 3 million,
Yeah.
right?
Yeah.
Okay.
they're also
Yeah, yeah.
gonna be spreading it in like.
Wait, hold on.
schools closed.
So,
That's like,
all right, let's look at D. So now D is going to actually address, I think, what Ms. Keegan was asking. Read part D. All of you, just read it. Don't start reading in the middle. So which equation are we going to use here?
350 million.
Which equation are we going to use for this problem?
Oh, and
What's this say here? Which equation are we going to use? Equation from B, okay, which is that one up there, right? So n of D equals 3.
I was just kidding, it was 160. I didn't mind
By 350, so that's 315, comma 00000. I think this is they probably did this up a few years ago when there were fewer people. I think there's more like 350, 360 million now, if I'm not
That's
mistaken.
not that many people.
Okay, so they want to know how long it will take, how many days it will take to reach 315 million. Well, what are we going to do here?
Plug it together.
Oh, wait, no, they didn't. Wait. How many days will it take? Yeah, okay. So we don't know logarithms right now yet. At some point you will do. We don't really have a way right now in this course to solve for a variable up in the exponent. Okay, you guys can't do that yet, not until we learn about logarithms. But so we're just going to plug in some number of days to see what happens. Let's try to start with some reasonable number of days. So
Well, I would.
look what happened after 20 days. How many?
Oh, I would, yeah, 200 because it's times 10.
200 days?
Oh, wait, no, 30.
Don't forget, it's doubling every
Yeah,
day.
yeah, so 30.
So
You should try 30. 25.
we'll start with 25. Let's try n of 25 and see what happens. Bless you. N of 25 is going to equal 3 times 2 to the 25. So everyone put that in your calculator and tell me what you get.
A lot. A lot.
Say the number. 100 million. 296 people. Are we at the 315 million yet?
No.
So maybe, should we, because what? Listen, every single day, this number gets what?
27.
Doubled, right? So let's try n of 26. See. Whoops. So it'd be 3 times 2 to the 26. Enter that in. What's our number? $592. 201 million. Okay. Well, on day 27, what's going to happen to this number? Can you just say it like without even putting it in? And so we'll go, but let's put it in and verify. So n of 27 equals 3 times 2 to the 27. And what do we get?
402,653,140.
What's that number?
402 million.
Okay. So somewhere in the 27th day, the entire population of the United States will know about this. Okay? So in 27 days. Now, of course, again, we're assuming like everyone that gets told, everyone that tells somebody tells a new person not no overlap, or, and that everyone bothers to spread a rumor, right? Okay? And by the way, these other calculators you use have that caret button too, so you can do them on here too. I just wanted to do that because I can't control them.
I don't know what's with the carrot button.
Now you know. So there's a lot of things that you don't know, and I'm guessing that's why you're in school.
I knew that because I messed around with the calculator.
All right, let's go to the next page. I got a question to ask you first. Hey, so that's exponential growth, right? Everybody agree that's exponential growth?
Yeah.
Something gets doubled or tripled, right? Or anywhere in between. Here's a question for you. This is just like purely theoretical, right? So don't even look in the book right now. Look at me. So at some point, this is going to seem kind of absurd, right? And as a practical matter, we'll have reached what we want. But I'm going to ask you the question: if I start out here, and I want to get to the door here, right? And if I travel halfway to the door, I've cut my distance in half, right?
That was not.
Whatever.
Like up here.
Okay? Let's just say I cut the distance in half. And now let's say I go again and I cut this distance in half.
Yeah.
Okay, right. With me? And now I'm getting closer, right? What's happening to the distance I cover? What's happening to the distance I cover each time I do it?
It's getting bigger, but you're.
Yeah, I'm covering half, but each of these halves are less than we were before, right? So now I'm going to go halfway again, right? And then I'm going to go halfway again, okay? And then halfway again. Will, it's a theoretical matter, will I ever reach the door by going halfway every time?
Yeah, no.
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 As a practical matter, sure, here I am at the door, I can reach my hand out and open it, right? But like, just in a strictly theoretical way, I will never actually touch the door if I just keep cutting the distance in half every time. It'll get small, the distance will get smaller, 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 but that distance will never reach what? Zero. It'll never actually go to zero, right? Does that make sense?
It'll be like 0.000000.
Yeah. Well, again, in the real, right, I'll get close enough in a practical sense that whatever I had to do with the door, I could do it, right? Yeah. So that's kind of what this problem is here. So we got this guy, it doesn't even matter, we don't even bother putting that in from Finland. What's the difference? So he's walking towards the White House, kind of like I was walking towards the door in a very cute, whatever.
Cutely.
So what's his starting distance from the White House? 160 feet.
That's a really short.
Anyway, it's not the
That's a
scale.
really tall guy.
So on his first trip, how much of the distance is he covering?
160.
Half of it. He's going halfway to the lighthouse on the first trip, right? And on the next trip, how much of that distance is he covering? Half. And then each trip after that, how much of the remaining distance gets covered? Half. So the distances he travels gets what every time? Shorter, right? Even though it's still half of what's left, it's going to be shorter, right? So we want to model his actual distance, D, from the lighthouse that is remaining after some number of trips, N trips. Huh? So somebody mentioned that this is not going to be exponential growth, it's going to be what? Decay. It's going to get smaller and smaller and smaller, right?
Brain cell.
But never actually reach what?
Yeah, I know.
0. All right, so these are convenient numbers, right? So before he takes his first trip, so on N of 0, he's 160. And what are we multiplying by each time? 1/2. So times 1/2 to get to 160 times, it's dividing by 2, right? Okay. So times 1/2 is 80, right? And then on the next trip, we multiply that by 1/2 and get what? 40 feet. And then we multiply this by 1/2 and get what? 20 feet. And then again, 10 feet. Are you noticing something different from what we're multiplying here? We're multiplying by a number that's what, smaller than 1?
Yeah.
And what's happening to the quantity we're interested in? Going down. Back here in the rumor one, we're multiplying by a number greater than 1, so it's growing. All right, keep that in mind. Because don't have a way to separate whether we're looking at growth or decay, right? All right, so part B. Each entry table can be found by multiplying the previous number. Previous by what number? We already kind of did that, right? So we're multiplying by 1/2 over and over and over again. We're multiplying by 1/2. Again, what handles multiplying something over and over again? Exponents, right? So let's go down here. So let's just kind of work this so we get into the previous page, right? So before his first trip, he's 160 feet, isn't he? So wouldn't that be really like 160 times 1/2 to the 0 power? What's 1/2 to the 0 power, everybody? 1. And so that actually equals 160. Oh, there's a typo here. That's not a 1. You guys see this? You guys catch the typo there?
Yeah.
So on the first trip, N is 1, this is actually 160 times 1/2 times 1/2, right? We'll just times 1/2 to the what power? For how many times? 1 time. Once multiplied by 1/2. 160, by the way, which equals 80. On the second trip, that's 1/2 times 1/2, right? Times 1/2 times 1/2. So that's really equaling 160 times 1/2. How many times? Twice, right? Cut in half and then cut in half again. On the third trip, that's 160 times 1/2. How many times? Cut it in half 3 times, which gives, oh, I forget, what's this equal? 40? And then this equals what? 20? And on the fourth trip, it's the original 160 cut in half how many times? 4 times, right? So think of the exponent as how many times you're cutting it in half. Or the other one, how many times you're doubling, right? Which gives us 10 feet. That make sense?
Yeah.
Okay. Well, let's write a an equation for this, like we did before. So D is going to be his distance as a function of what? Trips, which they want to use N for, right? So his distance as a function of his number of trips is going to equal, what was the starting distance? That's A I gave you before. Well, how about times 1/2? Go ahead. To the N power. Times 1/2, however many times he does it. Does that make sense? Huh? Well, you're on E already, okay. How far is he after 6 trips? Well, let's go to our calculator. Remember how I told you to put that 1/2 in? Parentheses, 1 divided by 2, right? So it's going to be D of 6, 160 times 1/2 to the 6. How far is he?
5
Push Control Enter. 2.5 feet, right? He's 2.5 feet from the windmill. Okay? So in F, he thinks he'll reach the windmill after 10 trips. So let's use our equation. So his distance is a function of 10 trips. It's going to equal the starting amount, 160 feet, multiplied by 1/2, how many times? 10 times. And is he at the windmill yet? Well, I want to use Control Enter again.
.15625.
Yeah. Say close enough, but 0.15625 feet, right? You see how the distance keeps getting smaller and smaller and smaller? But all we're doing is cutting it in half. You see how it'll never actually get to 0? I mean, we could go out and go to like thousands of zeros in the decimal, right? Theoretically. But again, at some point, he's practically at the windmill. He can do whatever he needs to do with the windmill, right? But theoretically, he's not going to get there. And there's a lot of things in the world that can be described with this, that the theoretical never reaching it is kind of important. The windmill, not so much. Yeah.
Why does it say lighthouse in the original problem?
I don't know. But yeah, is that what it says?
Yeah.
That's because it was just, who knows.
Maybe it is a lighthouse.
Maybe it's a lighthouse windmill.
It says lighthouse and then after it comes to people, so.
Yeah. B.